Hi everyone, I'm Tim Crundall. I'm an ANU astronomy student with Mike Allen as my supervisor, and I will be talking about the kinematic traceback of stellar associations, how we get fundamental ages, and we get quantitative memberships. Basically reuniting something. So my outline is I'm going to motivate why kinematic analysis is useful and important, what kinematic traceback even is, talk about recent precision improvements with the Gaia sunlight and what that does in the field, how we model and fit a group. I'm skipping this. I'm going to talk about preliminary results on synthetic data, and then priming those. So what is kinematic analysis? What are moving groups? So moving groups are sets of stars that were born out of the same gas cloud, but are no longer gravitationally bound. So what this means is they still retain a systematic kind of net velocity, but are distributed through space. That makes them hard to detect, because unlike Upper SCO and Centaurus, they kind of clump together in the night sky. TWA, the TW Hydro Association, kind of somewhat more spread out, so it's less obvious. Potentially detectable up to 50 to maybe 100 million years old. And so by analyzing all this astrometry, converting into galactic coordinates, we can get moving groups, their members, and their properties. What this means is that in the near future, if you've got the astrometry of a nearby star and its radial velocity at parallax, then you might be able to get a rough, like a quite good approximation. So I kind of already said that. So, but other purposes of moving groups fill is they can serve as test beds for stellar evolutionary models, because you've got the total range of stars that are precisely the same age, all that sort of stuff. They help paint a picture what conditions most stars form in. Groups like TWA, hyperplastic T Taurus stars, apparently that's useful for this evolution study. Accurate ages from time zero. So Mark over the weekend talked about how he's got different ages for stars. You've got the time since they entered the main sequence. But I think more interesting is the time from when the cloud, like the protostar, actually formed and accretion began. And so that will give you fundamental exoplanet ages. I like this table because it overinflates the significance of my work. This is a table from Soderblom 2010, basically a review on age techniques. And it labels all these other age techniques as model dependent or empirical. There's only two semi-fundamental techniques. There's no fundamental technique, but hey, here I am. Semi-fundamental only means of getting ages of pre-main sequence stars. So it's in the paper, that's true. So what is kinematic traceback? So basically what we need to do is take astrometry, position, parallax, proper motions, radial velocity, convert them into galactic coordinates. So here's our Milky Way galaxy, here's the center of the galaxy, here's the sun. Convert the measurements into XYZ UVW plane, carry over the correlations. So for example, uncertainty in radius gives you an uncertainty in X and Y, but they're highly correlated, so the actual volume of where that stuff could be is not as big as if you ignore the correlation. Then we trace it back. So we use Galaxy to project the orbits back in time around the galaxy. Here's an example of the Beta Taurus moving group. The green ellipses, so to orientate X is inverted, so looking up from the bottom of the galaxy, galactic center is over here, and the sun is about here. And so we've measured the green ellipses are where the measured to be now, and the blue line is their orbit back 20 million years or so, and the red ellipses are the possible location of each of the stars. So as you can see, it gets kind of messy. So in order to get around how messy real data is, I decided let's work on synthetic data. So generate a bunch of stars that are in fact formed in a Gaussian distribution of both position and velocity space. Project them forward in time from their original birth situation to where they would be now. Measure them with some degree of uncertainty, and feed that back into my fitting algorithm, tracing it back in time with the uncertainties. So I based my synthetic group on TWA, so it's got a similar age, so it's precisely 7 million years. TWA is about there, maybe. and its initial spatial standard deviation is 5 parsecs. So the whole volume is about 10 parsecs across. And pretending we have perfect precision, they start off here 7 million years ago and project back in time. Here's so that's X, Y, and again, they're both now, so here's a naive kind of estimate on the spatial distribution of these stars. So basically just fit like a Gaussian to that XY plane and take the standard deviation. And as you can see, it gets narrower at its original age, which is what you'd hope. So we're tracing these stars back, and where they converge the most is their point of origin. So, but that's for, barely any error. You can't even see the green ellipses, which is supposed to represent the current uncertainties. But we don't have perfect measurements. We're getting better measurements. So here's a brief comparison between Hipparchus and Gaia, which I don't have time for. Gaia's better. So here's what it looks like in the Hipparchus era. So you can see these uncertainties now, and try and tell me where the convergence is. You look back at just trying to apply a naive kind of analysis of the mean, like the standard deviation or the blue points at their furthest point back, and you can see it starts to diverge at 4.5 million years, and as quickly shoots off. Gaia, it's a little bit better. It's not so unreasonable, doesn't take up the entire screen, but it still does tend to uptick before its true age. And so people have tried to do kinematic age fits of groups like TWA, and here's kind of the struggle that they face, that it starts to diverge. I mean, you don't really have to know what these are. It's just like some proxy for the radius of the group at various times back. And it starts to turn upwards quite quickly. So the true age of TWA is around here maybe, but there's barely any convergence whatsoever. So is the data not good enough, or are we just not being clever enough? Bayesian analysis. So modeling the group origins. So we make some key assumptions. Basically, the stars become unbound instantaneously, and that moving groups can in fact be traced back to the smallest volume that correlates to their birth. And we presuppose group membership for now, but hopefully we'll get to the point where we don't need to do that. Here's our Bayesian likelihood, our model for the group. So basically, a group is a Gaussian in 6D space with a precise time that was its birth time. We fit with MC. I've got all these colorful animated things to explain how MC works, but I don't have time, so sorry, ask me later. And then hopefully you get like a corner plot like this, which tells you all your parameters and their uncertainties. Sometimes it looks like this, which isn't so great. It does look like this. Check your log plots, so they kind of look nice instead of have stuck stragglers. But yeah, all right, so results. What have we got so far? So on perfect data, the Bayesian fit lines up quite nicely, which is very comforting. I made this 4 hours ago, so that was a close one. On Gaia era, bear with me like this. It's a stochastic kind of thing, so there's going to be some noise. But it is in fact, so the true age is 7 million years, and the true initial spread is 5 parsecs. So, that's just fortuitous, but imagine it's getting pretty close. So that's quite promising. I've got 29 seconds left. Trying to use this on data as bad as back in the Hipparchus era. I mean, it's still doing pretty good. There's still you can see this trend of coming down and then the uptick happening after the true age. And if you were to kind of eyeball this by eye, I mean, I don't know how it's doing it. I'm supposed to know, but it's kind of magical. But because it's so magical, we're going to do some more tests on synthetic data and make sure it is in fact retrieving the true conditions, potential improvements. Well, so I haven't talked about what you do when you have stars that aren't in fact part of your group. So what we do other problems are maybe the initial conditions of the stars aren't perfect Gaussians. Maybe, they form hierarchically. And you need to kind of describe this multi-event process. And the most important thing kind of people want to know is, okay, sure, this moving group is so old, but is my star really a member of it? and calculate membership probabilities. So in order to answer all these three things is to fit multiple groups, multiple Gaussians, simultaneously to the same data set. So you can have multiple Gaussians mapping onto your association, as well as a bunch of Gaussians which will try and characterize these stars that aren't part of your group. And so that's called a Gaussian mixture model. If there's any people that recognize this term, just to give you a name. And the fitting algorithm for solving that is the expectation maximization algorithm. Basically, you have two steps. One is to have membership probabilities for each of your stars, fit your Gaussian fit each Gaussian in isolation to a weighted set of your data. So, you know, only characterize the stars that are like 80% most likely to be part of your membership, something like that. And yeah, and then test with incrementally more complex synthetic data in preparation for Gaia DR2, which is coming out in April. Woo! And that's all I've got. Thank you very much.